question 8, we have this equilibrium, and the first thing it asks us to do is to demonstrate that if we have this mixture, it's not at equilibrium. And of course the way we do that is by crunching these numbers to work out the value of the expression that should equal the equilibrium constant. If it doesn't equal the equilibrium constant, it means it's not at equilibrium. So let's write down the expression for the equilibrium constant first. So we've got Kc, and we just follow the normal things. Stuff on the right goes on the top, so it's Kc, and therefore we're talking about concentrations rather than partial pressures. So N2 times Cl2 squared, because there's 2 Cl2 there, divided by N2Cl4. So that needs writing down. Okay, you've got to write the expression down. It doesn't explicitly tell you to do that, but that's the basis for the whole question. Next thing is to recognize that these terms are concentrations, and the numbers you've been given are not concentrations, they're numbers of moles. So the next job is to convert these into concentrations, and of course you do that just by using concentration is moles over volume, and it tells you in the question that the volume is 2, so that's just moles divided by 2.00. So we've just got to divide each of these numbers by 2 to put them into this equation. So if we do that, N2 is 0.0319. If we divide that by 2, we get 0.01595 for the nitrogen. Chlorine is 0.0258. If we divide that by 2, you get 0.0129. And we've got to remember to square that, because it's chlorine concentration squared, divided by N2Cl4 is 0.142 moles. If you divide that by 2 to get the concentration, it's 0.0710 on the bottom line. And if you crunch those numbers, you get 3.74 times 10 to the minus 5 mole squared dm to the minus 6. And the question told us that this was the value of Kc at this temperature. Obviously these numbers are not the same. So that's the first thing you have to say, that this doesn't equal Kc, so it's not at equilibrium. It's important to actually write that down, because you may possibly not get all the marks just for crunching the number. You've got to explain what the number means, and what the number means is, because it's not equal to Kc, that you're not at equilibrium. What it also then asks us to do is to say, well, which way will the reaction go? And the way you do that is by saying, well, is this number that we've computed, is that bigger or smaller than Kc? And you can see, because this is something times 10 to the minus 5, but this is 10 to the minus 6, that this is a bigger number. It's very important to be comfortable with these powers of 10. 10 to the minus 5 is 0.0000374. It's got 4 zeros in front. This one has got 5 zeros in front. It's a smaller number. So we say that the value is greater than Kc. And if it's greater, it means the top line is too big relative to the bottom line. Okay, so we can say that. Okay, so top line is too big relative to the bottom line, and therefore to reach equilibrium the top line's got to get smaller, and of course the way the top line gets smaller is for the reaction to move in the backward direction. Okay, so that's the answer, that it's going to move in the backward direction, or to the left if you prefer. In part B then, we've just worked out that at the moment this equilibrium, it's not at equilibrium because we've got too much of the stuff on the right hand side, and therefore the top line is too big, and therefore the value of the expression is too big. So we can use that to say, well, if we've got too much stuff on the right hand side, the back rate is going to be higher than it would be at equilibrium. Remember, when you increase the concentration of something, the rate in general you expect to increase in some way depending on the rate equation. So if we've got too much of the stuff on the right hand side, which is what we have, we're going to expect the back rate to be higher than it would be at equilibrium. Equally, we've got too little of the stuff on the left-hand side, so the forward rate is going to be lower than it would be at equilibrium. So if we imagine this on a graph, which is the easiest way to visualize these things, if we plot the rates like this, then at the starting point where we are now, we've got too much of the stuff on the right, so the backward rate is higher than it will be at equilibrium, and the forward rate is lower than it would be at equilibrium. So the consequence of that is that the back rate is faster than the forward rate, as we can see, which is why you start to increase the concentration of the stuff on the left, because it's being formed quicker than it's destroyed. And obviously, as we increase the concentration of that stuff on the left, then the forward rate will increase. So to start with, it's too low, but it will start to creep up. So we'll get something like this. Equally, because the stuff on the right is being used up, right, because it's going that way quicker than these things are being formed, so the concentration of these decreases, and therefore the backwards rate decreases. So we're going to get something like that. And you can see if those trends continue, then what happens eventually is the rates become equal, and that's what equilibrium is. So if we continue those, we get something like this. And that would be the graph. And the point is, at that point, the rates are equal at equilibrium. Okay, so most of the time, the best thing to do is to keep ideas about equilibrium and ideas about rates separate, so you don't get confused. But really, equilibrium is all about the balance between rates. So just occasionally you have to think it through like this. And they're slightly harder questions because there's that sort of crossover involved. But if you can see that makes sense, then that's a good thing. So to get the mark, you had to first of all get that the backward rate was decreasing and the forward one was increasing, and then secondly that those rates became equal when you reached equilibrium. Okay, so part C asks us what happens to the amount of nitrogen in the equilibrium mixture if the pressure is increased. And crucially, it says that we have to explain the answer in terms of Kc. And when it uses that phrase in terms of Kc, it means you can't use Le Chatelier. Le Chatelier would give you the answer really quickly, right? So there are fewer gaseous moles on the left than the right, so if you increase the pressure, it will shift in the direction of fewer gaseous moles, which is in the backward direction. Therefore, the amount of nitrogen will go down. Unfortunately, if you write that down here, you get no marks, because it says explain in terms of the equilibrium constant. So you've just got to read the question carefully. Normally Le Chatelier is fine, and is the better way to go because it's so much quicker, but you can't do it in this case because of the way the question's worded. So what do we do in terms of Kc? Well, always when you get a question like that, the first thing to do is to recognise we're talking about the same temperature. The only thing we changed was the pressure. So the first thing you write down is that Kc doesn't change because the temperature doesn't change. And you will quite probably get a mark just for saying that, because that's the key to the whole thing. If Kc changed, then it would be a much harder question. So you've got to say that explicitly, not just imply it. You've got to say it. And then you think, okay, so what do we have to do to make sure that Kc doesn't change? And the way you think about that is think, what will happen to all of these concentrations if we increase the pressure? Now, increasing the pressure means we're squashing the molecules closer together, and therefore all of these concentrations will rise. So that's worth saying. Okay, so increased pressure will mean that all concentrations will rise, just because the particles are closer together. So what does that do to this expression? Well, the point is that on the top we've got concentration cubed, but on the bottom we've just got concentration, to the power 1. So if all of these terms get bigger, that's going to have a bigger effect on the top line than it will on the bottom line. If you're not convinced by that, just think about it numerically. Suppose we doubled the concentrations of everything. The top line would go up times 2 squared, which is times 2 times 4 times, which is times 8 overall, whereas the bottom line would only increase times 2. So that's really important. So we say that the top line increases more than the bottom line. because it has a higher power of concentration. Okay, that's just a nice succinct way of making this point. Okay, because it has a higher power of concentration. So what does that mean? Well, if the top line's got bigger more than the bottom line has, it means that the value of the expression is going to become too big. Right, so if we increase top line more than the bottom line, the value of the expression is now bigger than Kc. So we say that. It's not that Kc has got bigger. You've got to be very careful how you say it. We've already said Kc doesn't change. It's not that Kc's got bigger, but the value of the expression gets bigger. And what we have to do is say, well, what has to happen in order to bring that expression value back to Kc? And obviously the top line's got to get smaller. And the way it does that is moving in the backward direction. Okay, so reaction therefore shifts in the backward direction, or to the left if you prefer. Shifts in the backward direction to decrease the top line, increase the bottom line, and so return to Kc. And that's the answer. So at no point did we talk about opposing the change and all that kind of stuff. That's the Le Chatelier language that we couldn't use here because it wanted it explained in terms of Kc. But of course it gives the same answer. Le Chatelier says shift in the backward direction. This does as well. And obviously it's just alternative ways of reaching the same conclusion. But you've got to practice that kind of approach because it's not as straightforward by any means. So it takes a bit of effort to get that sorted out.